Hi, welcome back to Calculus. Today we're looking at section 5.1, area and estimating finite sums. So what we're going to be doing here is we're going to be estimating areas for curves. I have here a half circle on my board, and we're going to work with this here in this lesson. It's worth pointing out, we know what the area of a semicircle is. This semicircle has a radius of 2. The area formula for a semicircle is pi r squared divided by 2, and if you plug in 2 for r, you get 6.28-ish with some decimal places. But what we're going to do is we're going to, instead of just finding that area, we're going to estimate it. And this is going to be useful because we don't always know a formula for the area. So what we're going to do is we're going to work on estimating it, and we're going to see where that kind of takes us. So the equation for this semicircle will be x squared plus y squared is equal to 4. And when I solve for y, you can see I subtracted the x squared from both sides and then took a square root. We're just looking at the top of the circle, so it's just a positive square root, then a 4 minus x squared. So that's the equation we're going to be working with. So I'm going to redo this left-hand side of the board, and just kind of keep this number 6.28 in mind as we go through here, because we're going to do this example. We're going to use the same example a couple of times here. All right, so let's go ahead and do that. And yeah, I need a new board. Okay, so here's how this process works. We're going to be making rectangles using left endpoints. In this particular instance, we're going to use 4 subintervals, and I'm going to explain what all of that means. So first of all, the left endpoint. Well, actually, let's start with the subintervals. Subintervals just mean you take your whole interval, in this case from -2 to +2, and since I want 4 of them, I divide it into 4. Well, the total distance from -2 to +2 is 4 units, and if I want 4 subintervals, that means each one is 1 unit wide. So 1 unit, 1 unit, 1 unit, 1 unit. And you can see that down here when I find the areas. We'll get to that in just a second. Now, we're using left endpoints. There are other methods. You can use right endpoints for the subinterval. You can use midpoints, you can make trapezoids. We're just going to stick with left endpoints because this is an estimate, and as you would see if you tried the other methods, it doesn't make a whole lot of difference which method you use. So for this first rectangle, it's not even a rectangle. In fact, let me start at the right-hand side and work my way back to the left so we can see what we have. At the right-hand side, we have the subinterval from 1 to 2. Its left endpoint as a coordinate on the graph of 1 square root of 3. So I just make a rectangle that has that width of 1, because that's the length of my subinterval, and the height of the square root of 3. So that it's using that left endpoint where it hits the graph to make my rectangle. And so that's my fourth rectangle down here. It has a width of 1, it has a height of square root of 3 for an area of the square root of 3. And you can see that particular rectangle is an overestimation of the area, right? It's got more area in there than is actually just under the curve. And the same thing happens here with this third rectangle, because I went from left to right when I labeled them. This one also has a width of 1. All the subintervals will have the same width. This one has a height of 2, because at 0, the y value is 2. And so that area is 1 times 2 is 2. For the second one, again working backwards, its left endpoint is at x equals -1, which has a y value of square root of 3. So again, we get a width of 1 and a height of square root of 3. These two rectangles ended up being exactly the same, but notice now this rectangle is an undercount of the area. Right? This one was too much, this one's too little. And that's okay. The idea is that it should hopefully balance itself out and get us a pretty good estimate. Which brings us all the way back to rectangle number 1. Notice rectangle number 1, this subinterval has its left endpoint as -2. Well, the y value at -2, if you plug it in, is 0. So this is a rectangle with no height. And so we have a width of 1 times 0 height, and that rectangle gives us no area, which is definitely less than what the area should be there. But notice then, if I add it all together, I have a 2, and I have 2 squared, it's a 3. And if you type it into your calculator, you get 5.46. And that's a bit smaller than the 6.28 that we know is the actual area. So the question then is, how can we make this a better approximation? Well, we make better approximations in large part by using more subintervals. And that's going to be the next one. The next time I'm going to do this exact same example, but we're going to do 8 subintervals instead of 4. So hang on and let me get that on the board. Alright, so here's our second attempt at finding the area, or I should say, at estimating the area under this half circle. So notice this time I broke it into 8 subintervals. So there are 8 little rectangles here going across. I'm still going to keep using those left endpoints. So now my x values are at -2, -1.5, -1, -0.5, 0, 0.51, 1.5, and then we end up at 2, but that's not a left endpoint, so we won't be using it to make our rectangles. And you can see I did the exact same thing. This time my rectangles have a width of 1/2, so all of these have a 0.5 here to start the multiplication. And then all I did was I plugged in the x values on the left side of each rectangle to get this list of second numbers that we're multiplying by here. 0, 1.32, square root of 3, 1.94, 2, 1.936, square root of 3, and 1.32. It's a mess. There's a lot of rounding and estimating going on here. We are working with square root functions, so it's going to be pretty nasty. And you can see all the estimates that I got for all those products. When you add them up, you get about 5.99. So I think you guys can do this. This is really pretty straightforward. Just be careful. And yeah, be careful. And we can do this with any curve. Okay, so it doesn't have to be a nice semicircle. We dig in an area that's a lot closer to the actual area of the semicircle this time. Still not there. We could keep going. We could keep shrinking these, and that's kind of actually where this is headed here in the next couple of sections. Except that this is the only time we're going to have to do this kind of just tedious grunt work of, here's my rectangles, let me add them all up. This is messy. There are better ways. So anyway, that's finding the area under a curve using left endpoints. Like I said, you could also use right endpoints for each interval. You could use midpoints, so you'd have to find the x value at the middle of each of those rectangles. You can make trapezoids, so you have to use the formula for the area of a trapezoid, but basically then you connect the two endpoints, or the dots on the curve for the two endpoints, and make a trapezoid out of it and add up all the trapezoids. It's all tedious. We're going to do the left endpoints, so if you're taking my class and you're watching this, when you do the homework, just do it with left endpoints. We don't have to worry about anything else. This is fine. All right, so thanks for coming. Have a wonderful day, and I'll see you in the next video.